Hey Mustangs, in this video we're going to be taking a look at what affects reaction rates for chemical reactions that involve enzymes. Now before we start, we need to make sure that you understand what we mean by reaction rate. So when we talk about reaction rate, we're talking about how quickly are we changing substrates into products. So how quickly is that happening? Now when you take a look at the graphs that we're going to be looking at in this video, when you start towards the bottom here, when we're looking at reaction rate on our y-axis here, towards the bottom we're saying that very little substrate is being converted into product. The higher you go up, we're saying a lot of substrate is being converted into product. So as you move up the y-axis, we're saying more and more substrate is being turned into our products. There are many things that can affect reaction rate, how quickly we can change substrate into product. So two of them are going to be based on concentration, enzyme concentration and substrate concentration, and then there's going to be three other factors that can affect it as well. So let's go ahead and take a look first at enzyme concentration. So when we add more and more enzymes, so as we go along the y-axis here, we're saying we're adding more and more enzyme. So we add more enzyme, more enzyme, more enzyme, and we see that we get a line that looks like this. And basically what we're saying is, as you add more and more enzyme, you're able to make more and more product. You're able to convert more and more substrate into your product. And it makes sense because if you have a lot of enzymes, the more enzymes you have, you're going to be able to grab more substrate and turn it into your products. But you see when you get towards the top here, it starts to level off. And the reason that it levels off has to do with the fact that you get to a point where you have so many enzymes, but the substrate is limited. You only have so much substrate. So you get to a point where all of the substrate is bound to enzymes and are being broken apart and turned into product. And if you add any more enzymes at that point, those enzymes are kind of just sitting around doing nothing. There's nothing for them to do because there's no additional substrate for them to work on. So we see our curve kind of go up and then level off, so we can make more and more product, but eventually we get to the point where the substrate becomes a limiting factor. There's just not enough substrate for the extra additional enzymes, and you're not going to make any more product at that point. Substrate concentration is very similar. So here, as we look at the x-axis, as we increase the amount of substrate, as we add more and more substrate, we're going to see a very similar line. Okay? But here, what we see happening, we add more substrate, and as we do, we can convert more substrate into product, which makes sense, right? If you have a lot of your beginning ingredients, you can make more product in the end. And that's what we're looking at here. You add more substrate, you can make more and more product as you add more substrate. But once again, we see a point where it starts to level off. Here, what's happening, as you've added more substrate, all the enzymes, you haven't added more enzymes. So the number of enzymes has stayed the same. Eventually, you get to a point where all the enzymes are being used. At that point, we say that the enzymes are saturated. All the enzymes are bound to substrate, and any more additional substrate you add has to wait in line in order to be broken apart and turned into product. So here in this case, the enzymes are the limiting factor. It's the enzymes. They're stuck at a certain number while we add more and more and more substrate. But eventually, all the enzymes are in use, and all the extra substrate has to wait in line until the enzymes release the substrates that have turned into product now, and then they can bind. So here, the enzymes are the limiting factor. All right, next we have temperature. So again, you have to think about what reaction rate is. How quickly can we turn our substrate into product? So here with temperature, we see a line that looks like this. When we're talking about temperature, you have to take into consideration how the enzymes are floating around, the substrate's floating around, whether it's one piece that's a substrate or multiple pieces that are a substrate, and they have to run into each other. So that's something you have to consider here. You know, they don't have eyes, they can't look around for each other. They have to run into each other in order to come in contact and for the chemical reaction to happen. So when we're talking about temperature, you have to remember what temperature is. Temperature is how quickly the molecules are moving around. So at high temperatures, molecules are moving around very fast, so they're bouncing around everywhere. When you're talking about low temperatures, molecules are moving very slowly. And when you're talking about freezing, the molecules are basically standing still. Okay? So here with temperature, when we take a look at the graph, the reason why we see this curve go up and then down is when you start here, at cold temperatures, the possibility, so especially towards freezing, the possibility of the substrate and the enzyme coming in contact with each other, running into each other, is very low because they're moving around either barely at all or really slowly. So that decreases the chance. But as you increase temperature, that's what we see with the line here. You increase temperature, well, the molecules start to move around faster and faster. They're more likely to collide with each other. And as a result of that, you're more likely to turn substrate into product. So as you increase temperature, you're more likely to turn substrate into product. So we increase the reaction rate here. For all the different types of enzymes, each one has what we call an optimal temperature. The best temperature to have the most likely collisions. And that's what we see here at the top of the curve. That's where you're going to have the most collisions, and the enzyme's going to work great. So you're going to have a lot of substrate getting turned into product. But once you go past the optimal temperature, and we see it drop off all of a sudden here, the reason for that is once you get past the optimal temperature, they're colliding with each other, everything's happening, everything's all good, but past that point, you start to denature the protein. So the temperature gets so hot that the bonds in the protein that make its 3D structure, the weak bonds that hold the enzyme together in its 3D structure, start to break apart. So past the optimal temperature, the reason we see this drop off, you start to make less and less and less substrate to product, is because you're denaturing the protein, you're denaturing the enzyme. So all these enzymes are changing shape, they're unfolding, and if the enzymes are unfolded, they can't do their job. So you make less product as a result of that. All right, next we have pH. So with pH, we get a very similar curve to what we saw with our temperature. And with pH, there's also an optimal pH for different enzymes. So in humans, a pH of about 7 is what we see as the optimal pH for most enzymes in humans. Now, when you're taking a look at this, you have to take into consideration what we're talking about when we talk about acidic versus basic. So it all comes down to hydrogen ions. So hydrogen ions with its positive charge here, as you go towards the more acidic side, because remember 7 is neutral, as you go towards the more acidic side, we see that you find more hydrogen ions. As you go towards the more basic side, you find less hydrogen ions. Now, looking at hydrogen ion, it has that positive charge, that can interfere with weak bonds that form the 3D structure of your enzyme. So here, since most of our enzymes have a pH of 7, or work at its optimal of a pH of 7, you see that if you go more towards the acidic side, you're increasing the number of hydrogen ions. So that basically starts to break down and denature the enzyme, and so you produce less and less and less product as a result of that. So you turn less substrate into product as you go towards the more acidic in this case. So this enzyme has its best shape in this case at a pH of 7. As you go more towards the basic side, you're reducing the number of hydrogen ions, and that can affect the bonds within the enzyme as well. So as a result, in this case, it can denature it as well. It can unfold and it's not going to work. So again, as a result, moving away from the optimal pH, you produce less and less and less enzyme till eventually it's denatured, so you can't produce any product at all. Now, in humans, most of our enzymes prefer a pH of 7. That's their optimal pH. But in different parts of the body, there's different conditions. And certain enzymes hold their shape better at certain acidities, certain pHs. So here, in this case, the enzyme called pepsin that's found in the stomach, its optimal pH is almost at about 3. So here, that's when the protein is going to have its best shape. It's going to be the correct shape to do its job. As you move away from it towards the more acidic side, you add more and more hydrogen ions. That's going to interfere with the bonds within the pepsin enzyme. It's going to denature the enzyme. As you move more towards the basic, that has less hydrogen ions, that's going to also interfere with the bonding in the enzyme, and that can denature it as well. Last here, we have trypsin. In this case, this is an enzyme in the human body that's found in the small intestines, and this one prefers a more basic pH. So here, its optimal temperature there, not temperature, my bad, its optimal pH is going to be a little bit below 9 here in this case. And again, as you move away from it, you're going more toward the acidic side, you're increasing the hydrogen ions. That will interfere with the bonds within the enzyme, break it apart, denature it. As you go more towards the basic, that decreases the hydrogen ions. That's going to affect the weaker bonds that hold it together and denature it that way. All right. Finally, we have salinity. So with salinity, we have a very similar curve once again. So we see that reaction rates increase. We can produce more and more substrate to product up to a certain point, and then we see it falls down where we start to produce less and less substrate to product. So here, again, we have an optimal salinity for enzymes. So to take into consideration here is cations and anions, so positive and negative charges. When you add salt, it can dissociate and you have positive and negative charges form. If you remember, many of the R groups or the side chains of the amino acids can have positive or negative charges. So these extra positive and negative charges that have been added can interfere with the R groups and cause denaturation, cause the protein, in this case the enzyme, to denature. So here we can see we have an optimal salinity, and as you go away from that, where you decrease the salinity, there's not enough positive and negative charges for the enzyme that it actually starts to break apart. This way, you are increasing the amount of positive and negative charges, and that interferes with the weak bonds and can break it down, denature it that way. So you can see there's just that optimal salinity that your protein's going to work at. All right, that's it for looking at reaction rates and protein and enzymes.